Alright everyone, welcome back. This is the last day of Green's theorem. I assigned an assignment yesterday, and maybe some of you guys didn't turn in yet. It's okay. I wanted you to show that this was equal to this for the problem on the last page, which was up here. So if you need to pause and write that problem down again, you can, and then do that. The only thing I'm going to show you right now is that for each of these integrals, you should be getting 2 pi as an answer. So in case you were wondering if you did it correctly or not, those would be the values that you should end up with. Okay, so anyway, moving on, I want to do a couple problems with you guys again. Maybe this will help you also. So let's look at example 4 here on my note sheet. Evaluate the integral xy dy minus y squared dx, where C is a square cut from the first quadrant by the lines x equals 1 and y equals 1. Okay, so first quadrant, x equals 1, y equals 1. So that's our square there. Again, this would be a pain to do because to parameterize this, you'd need 4 different equations to move around this square. So this is a perfect example of where using either the divergence integral or the k component of curl or the circulation integral will work in our favor here. So first things first, we have to identify the kind of question this is asking us. So you have to look at this, and honestly, flux and circulation, if you rewrite them, you can change and manipulate it so that it works for what you want to do. So by looking at this one, I have something dy minus something dx. Well, if I look up here, the flux integral is m dy minus n dx. So this is actually asking for flux. You could have turned it around and rewritten it and done it with circulation and the k component of curl, but we don't have to do that since it's set up as a flux equation. So this is saying this is m, and then this is n, and that this is a flux. That's important to know before you do the problem, because you want to know which integral you're doing. Okay, so the good news is we're not going to use the curl integral, we're going to use the divergence integral. So to do divergence again, for flux, this is what I did with you guys yesterday. You need the derivative of m with respect to x, which is just y, and you need the derivative of the n piece with respect to y, which is 2y. Okay, and remember, divergence is just adding these two together. This negative sign is not a part of the divergence integral. It's part of the flux equation, actually. So we can rewrite this equation now as the integral over the region of the divergence, which is just adding those two pieces together, and then dy dx or dx dy. I'm going to do dy dx. It doesn't matter. So the region for x and y go from 0 to 1 and 0 to 1 of 3y dy dx. So this is now my new flux equation, except for, again, it's a divergence integral. But see how easy this is now to evaluate? Instead of parameterizing 4 curves and doing all that crazy stuff with r of t and subbing everything in, this is way easier. So let's do some quick double integral. This is 3/2 y squared, which just turns into 3/2. So we get 3/2 x when you integrate it again, which means that the flux is 3/2. And that's it. My point is, though, I kind of want to show you guys real quick that you can rewrite it as circulation, okay? If you rewrite it as circulation, it's m dx plus n dy. So if I rewrite this, m is now with dx, so I'm going to put a negative y squared dx, and then it's plus n dy, so this would be xy dy. This is now counterclockwise circulation, as opposed to this, which was just flux. So in this case, my m would be this, my n would be that, and then I can turn it into this curl integral. So you could do it that way and do circulation. However, since it was set up to do flux, because it was already nice and set up for flux, you can just use flux, or the divergence integral. Okay, let's do one more problem. Oh, I have, I guess, the answer there. 1 second. Okay, so I'm back to this problem. It's erased now. Calculate the outward flux. So I'm already telling you I want flux for this problem. So I'm starting with the problem where we have the setup m dy, although this doesn't even matter, n dx. That's what flux is. All we need to know, though, is we need to turn it into this integral here, the double integral. Sorry, that's a terrible integral symbol. Of dm dx plus dn dy dx dy over the region. So the region is a square now that goes from -1 to 1. I'll pretend that's a nice square there. Okay, so that's our region. So to find the flux over this, we need to just find our missing pieces. Again, if it's set up like this, m dy minus n dx, well, we don't even have to look at that. This is m and this is n. So m with respect to x is equal to 1, and n with respect to y is equal to 2y. So my integral becomes the integral from -1 to 1. Why am I doing that? Alright, there we go. -1 to 1 for both of them, of the sum of these two pieces. And then that's dy dx or dx dy. Doesn't matter since they're both the same. Alright, at this point we have it set up. This is the flux, the divergence integral that will give us the outward flux of the field across this square boundary. So let's keep solving. I'm going to integrate with respect to y first. Alright, and then we get that, y plus y squared. When you evaluate that from -1 to 1, when you put a 1 in, you get 2. When you put a -1, you actually get a 0, because that will become positive and then it'll become negative, so it cancels. So you actually end up with the integral from -1 to 1 of just 2 dx, which is equal to 2x evaluated from -1 to 1, which is equal to 2 times 1 minus 2 times -1, which is equal to 4. So the outward flux would be 4 in this case, using our divergence integral. Okay, so hopefully you guys see, again, how nice it is to be able to turn the things we did in 7.2 into a double integral over the region. Alright, so your assignment tonight, and I know I'm going to post it on the Canvas page, but if you wanted to see what the problem looked like, it's basically the first problem on the next day of notes. Oops, I thought it was here. Hold on 1 second. Here we go. I want you guys to do this problem. This is normally a note problem I do. I have it set up. This time the area is going to be the region bounded by this triangle with these 3 points. So a little hint for you guys: draw the region, figure out the equations of the different lines, and set up your bounds of the double integral like we used to in chapter 5, and those will be your bounds. Also identify which one this is. This could be circulation, this could be flux, depending on how this looks. So look at your notes and see which one you think it is, and then go forward from there. Good luck. And again, if you have questions, always email me, or again, I'm probably going to, after this section, have another video conference to kind of go over any problems you might have had. Have a good day.